In this problem, we have a bullet being fired into a block of wood. It's broken into two parts. You see a couple ways that this bullet could collide with a block of wood. So we'll start with the first part where we have the bullet passing through the block. When we're setting up momentum problems, we're really looking at the concept of conservation of momentum. All right, so let me draw a picture first. All right, if I'm visualizing this correctly, I have a bullet being fired. And we got this block of wood sitting here being about to be hit by this bullet. When we talk about collisions between two objects, they would be our system. Right? You have a mass of the bullet, and you have this mass of the block. And when we look at a system, the momentum of our system before a collision is equal to the momentum of the system after the collision. And that's true because if we're considering our system of the block and the bullet as our masses, there is no external force acting on those two objects. And so any forces between them are considered internal with the system. And so we can say that momentum is conserved. All right, so when we look at this, the before scenario is what I've drawn here. And I'm going to draw kind of a therefore 3 dots. And I'm going to show what's happening after the collision. Well, after the collision, the block is now here moving, I'm assuming, to the right, and this bullet has passed through and it still has some velocity. And in my picture I can draw some of these values. I know the mass of the bullet. Let me put the velocity in here. This is 220 meters per second. It says the block is motionless, so I know this is not moving. It has no momentum. After the collision, we have a new velocity. Let's call this v of the block. That's what they're trying to find. And we have a bullet that has slowed down. It now has a velocity of 150 meters per second, right? So I have this picture. And notice how I try to draw the arrows. The arrows are our velocity vectors. We try to draw them to scale. The most important one here would be that the two bullet arrows are not the same length. I might even exaggerate it and draw this one on the right a little slower to really show that the arrow has gotten shorter. This bullet has lost momentum. Well, if the system's momentum is conserved, where has the bullet's momentum gone? Well, it's gone into the block, right? And so now we can set up a calculation and actually see what that velocity of the block would be. All right, so if I take this original system before, system after, well, that's going to be the momentum of the bullet before, call that initial, plus the momentum of the block before the collision. I'll put a little I there. And conservation momentum suggests that after the collision, the bullet will have a new final velocity, momentum, and the block will also have a final momentum. But the sum of those two momenta will be the same. And we have an equation for momentum that says P equals mv. So I can take it another step further and say the mass of the bullet times the velocity of the bullet at the beginning plus the mass of the block times the velocity of the block at the beginning would therefore have to be equal to the mass of the bullet at the end. I'm sorry, there is no two different masses of the bullet, so we just mass of the bullet, but the velocity of the bullet at the end plus the mass of the block and the velocity of the block at the end. Now, if I'm doing this problem, it may make sense to call one object A and one object B, or call it the bullet number 1 and block number 2, and you can see these subscripts would clean up a little bit. You wouldn't have to read my chicken scratch. But nonetheless, we can start plugging in values. So what I do know here from the problem is I know the mass of the bullet is equal to 11 grams, and the mass of the block is equal to, they give us the mass of the block, 500 grams. Now, a good habit would be to convert this to our SI unit of kilograms. We would do that by dividing by 1,000, which would be 0.011 kilograms, and 0.5 kilograms for the block. We know the velocity initial for the bullet and the velocity final for the bullet are given. They're both to the right. I can write that in here with my notes. In fact, I'm just going to put it right here right on my picture, V final. And now I can plug in some values. All right, when I plug in the mass of the bullet, I have 0.011 kilograms, and its initial velocity is 220. I'm going to put a little plus sign there just as a reminder that we want velocities to always have a sign. The mass of the block is 0.5 kilograms, but it has no velocity. So actually that piece cancels out. There's no momentum. The whole system's momentum is the bullet. Later, though, the same bullet now has a new rightward velocity of 150. And now our mass of the block, 0.05, has a final velocity of the block. Right? So when I've plugged everything in, it's clear that I can solve for the one missing piece to find the velocity of the block after the collision. So now let's pull out a calculator here and start plugging some things in here. The system's momentum would be the mass of the bullet and its initial velocity, which is 2.42. So the left side becomes 2.42 is the momentum. That would be in kilogram meter per second squared. If everything's in kilograms, meters, and seconds, the units will work out. If I take 0.011 times 150, I get the new momentum of the bullet, 1.65. And there's a difference there. There's a change in momentum due to the block pushing on the bullet internally with that system. Well, that means the block would gain that difference. So I'm going to continue writing out the rest of this equation. And there's the velocity of the bullet. And now we're solving here. So if I take 2.42 and I subtract the 1.65, we would get 0.77. And that is the change of momentum of the bullet. Right? This is P initial for the bullet. This is P final for the bullet. I'm subtracting it. And I would get a change in momentum. It's lost. It would end up being a negative number of change in momentum if I did P final minus P initial. But ultimately I get this. I'm going to divide both sides by 0.5. And I get 1.54. The velocity of the block is equal to 1.54 meters per second. All right, so here's this block that had no velocity, and this bullet's fired, it passes through, and now it's gained a velocity of 1.54 meters per second. So here's a pretty simple collision here where the object passes through. But what happens if this bullet actually was lodged in the block? Well, let's look at that same equation, except what we don't know is how fast the bullet is afterwards. But if we set our equation up in the same way, the left side remains the same, right? You still have the same bullet. I'm going to rewrite my subscript. I'm going to say the mass of the bullet, velocity of the bullet, and I'm going to say mass of the wood and the velocity of the wood at the beginning. That'll make it a little bit easier to track the different variables. After the collision, you have a mass of the bullet and the velocity of the bullet at the end, and the mass of the wood and the velocity of the wood at the end. However, something's different about this collision. This bullet has stuck into the wood, meaning they are moving together. And so when you have these types of collisions where the objects stick together, then you can infer that they would have the same velocity. We would know that V bullet final is equal to the velocity of the wood at the end, and so we can just call that V final. So the right side of this equation becomes mass of the bullet times V final, plus the mass of the wood block times V final. And any algebra teacher would tell you, well, why don't we factor out that V final? And you get something that looks like this. MB plus the mass of the wood block times V final, right? You get this grouping. And it actually looks like what's happened in this scenario. They are stuck together. And so it's not a new equation. It's just simplified algebraically. And it actually looks like what's happened in this situation. Two separate objects now becoming one object. And so now I can start plugging in numbers. The left side of my equation hasn't changed from above. It's still the same original momentum. So I'm just going to carry that number down that we already calculated. But now I'm going to add the mass of the bullet plus the mass of the block and multiply it times their final velocity. So I'm going to get 2.42 as the total momentum of the system. And when I add that, I'm going to get 0.511 times V final. And so the last step would be to divide by 5 0.511, and I'll get a new velocity. I get 2.42 divided by 0.511, the total mass of the bullet in the block, and it's 4.73 meters per second. All right, so here we see in this second type of situation, we get a bullet passing through in the first one, and the block doesn't gain much velocity. But here in the second, the block's going to gain a lot more velocity in this situation, right? So a good example of two types of collisions between a couple objects, setting up using conservation of momentum to set up our equation and finding the missing piece.